strange thing I noticed with this phone is that if I don't pause it, just start it up and let it run, that after it completes one file, it'll stop. But if I pause it and then start it up again, it will just move on to the next file and one fills up. I don't know if eccentricity of the phone or a warning sign that the phone's getting ready to crap out. I have a mass of 5 kilograms, cruising along at 4 meters per second. What is the kinetic energy? Pardon?
20. 5 times 4.
That would be the magnitude of the momentum. I think we forgot to square something. 40? There we go.
I did.
Oh, I'm about to ask a question. Mentally prepare yourself. Here we go. What's the formula for kinetic energy?
1/2 mv squared.
So that's 1/2 times 5 times 4 squared. 40 what?
Joules.
That works. All right. Simple enough as long as you have the formula and you don't make a careless error. Plug and chug. Let's make it more complicated. I have a long stick with a pivot down here. Or you can think of it as you're looking at a door from overhead. As the door swings, or as the stick falls, what's the kinetic energy? Let me give you some mass here. How about we got a 10 kilogram mass. And let's say that at this point right here, it is swinging at 5 radians per second. I'm trying to remember if we've done radians per second in this class or not.
No.
Okay, let's talk about radians per second. What's a radian?
Half the diameter?
Pardon?
Half the diameter?
No,
Oh.
that's the radius. The radius, not the radian.
Mm.
All right, so pretend that's a circle. How many degrees are there in an entire circle?
60.
360.
Why?
That's what they say.
Who? Who's the group that we can blame for 360?
Somebody, his name begins with C.
Geometers,
Well, the group's name.
mathematicians.
Oh. Not really mathematicians at that. Well, priest mathematicians, they probably were in that society. The Babylonians. It's the group. All right, the Babylonians are to blame for 360. Now, why? There's the idea of sort of ideal shapes, and they recognize that an equilateral triangle had there's something special about equilateral triangles. And even later in the Babylonian society, in Greek society, they started to think of everything was made up of these perfect shapes. But equilateral triangle was a special shape because all the angles are the same and all the sides are the same. And also 60 was an incredibly important number. Babylonians had a base 60 system, whereas we're base 10. They were based at 60. And mathematically, 60 is really a nice number because it is divisible by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. It's divisible by a whole slew of numbers. Morning. And so they mesh these two ideals here with each of these being 60. And then they recognize that if I take 6 of these triangles here, it sort of forms, it's actually a hexagon, but you basically are going all the way around. And so I have 60 here, 60 there, etc. And so I have 360. At some point they stuck the units of degrees onto it, but that's where it comes from. It is man-made. Mathematicians wanted to free us of this. They wanted to come up with, is there anything natural to all circles? Is there a natural unit we can use for angles? And they realized. What is one thing all circles have?
No corners, no sides.
I would agree with no corners. Or it has an infinite number of corners for some people who have read Flatland. Sorry?
I said a center point.
You have to be louder.
A center point?
Okay, they have a center point. That is true. And
Radius, diameter.
radius is the one I was hoping for. Yeah, there is a center point, and the distance from that center point to every point on the circle is the same in the radius. So this is something natural to all circles have a radius. And then if I take that, so imagine I got a circle here, I have this length right here. Imagine it's a piece of string, and I take that string and I start wrapping it around the side. It turns out for every circle, if I take the string the length of the radius and I start wrapping it around the side of that circle, it always gives the exact same angle. Every circle will do this. The radius of that circle will subtend the same angle. And that, they figured, was natural. That is sort of, yeah, natural. That is what nature is providing with us, and they decided to call that 1 radian. So now the next bit is, well, how many radians are in an entire circle? Well, the question, since this arc length here is the same as the radius, the question is how many radiuses, properly, how many radii are there around the circle? Well, what's the formula for all the way around the circle?
2 pi. 2 pi r.
The circumference of a circle is 2 pi r, which means that the radius will go around 2 pi times. So that's why there's 2 pi radians. It's the same as 360 degrees. All right, questions to hear? So there's going to be some relationship here that we will need at some point relatively soon. Between, if I have this thing spinning, it has an angular speed. If it's a rigid circle, then as it spins around this point right here, it takes as much time as this point right here to go all the way around the circle. So imagine I got a disc. I got 2 points on it, and they're traveling around the circle in the same amount of time. They have the same angular speed. Think about regular speed. What is the formula for regular speed? Is that what you said?
No.
That's, you could have lost your way through that one. It's distance over time. Angular speed is very similar to it, in the fact that it's the angle divided by time. So if I take a circle, or I have, you know what, let me go grab a prop. I'm just gonna let that run. All right. That's wrong. All right, so I got these two pieces of paper on here, and as I spin it around, it takes the same amount of time to go around. Matter of fact, we could figure out how fast what the angular speed is just by timing how long it takes to go around once. Let's just assume that we timed it beautifully, and the time it takes to go around once. That's the symbol for period. I think we have dealt with period before in this class. Getting some heads shake no on that one. So period for repetitive motion. The period is the time to complete one cycle. Or one of whatever is being repeated again and again. So as it spins around, it's going around the same circle again and again, and so the period would be the amount of time it takes to go around once. It's what you were finding in the centripetal motion lab when you figure out how much time it takes to go around once in order to be able to find the speed. So let's say that the period was 0.3 seconds. The angular speed, therefore, would be, well, in going around once, the angle is 2 pi radians. And the time is 0.3 seconds. And so 2 pi over 0.3, whatever that is, a little bit more than 20-ish.
You said 2 pi divided by 0.3?
Yes. 9.4. And then the units would be radians per second. However, questions there before we bring in linear speed? All right, so I have these two pieces of paper that have the same angular speed because it takes the exact same amount of time to go around the exact same angle. Which of those two pieces of paper is traveling faster?
The one closer to the center.
Why?
It's not covering that much, I guess. No, that's probably not the right word. I don't know.
The paper that's at the end, because it's further away from the axis of rotation.
So you say the one farther away Why?
It's moving faster because it's further away with the axis of rotation.
Which means what? Because it's farther away, what's happening?
There's more distance to cover?
Yes, your reasoning was almost there, but this is traveling farther distance.
Oh, that's the misworded question, I'm sorry.
Okay. So there's a relationship. The farther away I get, the more distance I have to cover, and so there has to somehow be a relationship between my angular speed, my linear speed, and how far it is away from my axis. So if I'm talking about the time it takes to go around an entire circle, my linear speed would just be my distance over time, as said earlier. The distance is just the circumference, because it's traveling, that's the length along the edge of a circle, so that's 2 pi r, divided by the period. Well, 2 pi divided by the period is the angular speed, this part right here, and so this is just omega r. So we have, the important part here is that the linear speed is equal to the angular speed times how far it is away from the center. And supposedly there's a children's game. You have people stand in a line holding hands, and then the person in the middle just starts moving slowly, and everyone tries to maintain the line. The farther you are out, the faster you have to go in order to maintain the line.
Maintain the line and keep going slow as the first person?
The first person has, I can turn around like this. If we all joined hands out in the field and did this, I can move like that, and that person on the farthest out is gonna be running full sprint.
Really?
Yeah, there would be. We got enough people in here. That'd be a really long line.
Okay.
Can you repeat what we just said?
You're pointing over here, what I said about this. The relationship between the linear speed, so the speed that we're dealing with in chapter 3, the relationship between the linear speed of this piece of paper and how fast it's rotating is summed up in this relationship right here. That the linear speed of some point in something that's rotating is equal to the angular speed times how far it is away from the center. So the farther you are away, the faster you have to go.
Now, why is the W a W?
It is an omega. There's a pattern that a lot of rotational things that deal with rotation, they use the Greek letters. So it's a lowercase omega. Did that answer your question? Okay.
Thank you.
All right, I think we can get back to the closing door of the falling stick. All right, I have a stick. As it falls, it's rotating. How would I find the kinetic energy of it? If I know how fast this point is moving, the other point's still, so that stick that's falling over, so it's rotating about like that. If I know that this speed at this point is, I think, 5 meters per second, and the mass of this is 10 kilograms, what is the kinetic energy?
Do I need to factor in the mass?
Kinetic energy does factor the mass into it. You plug it into 1/2 mv squared.
So I didn't do that.
You get 125 joules if you plug into that, so 1/2 times 10. Yeah, okay. However, if this stick is falling like that, this point here is going 5 meters per second, how fast is it going in the middle?
Half of that speed?
See?
Half of that speed?
Yep. If I'm at half, if R is half of what it was, then V gets cut in half also. Omega is the same for every point on that, assuming it's a rigid body. So when plugging into this formula, should we use 5 or 2.5? Or a different number? Turns out it's a different number.
I was about to say a different number, but I just wanted to say that.
Oh. Did I ask again? Did the setup?
No.
Okay. So how do you deal with something that's rotating because not everything on it is traveling the same speed? That, I'm going to go through the derivation because everyone loves a derivation. Can't have too many letters on the board. I'm going to go through it mainly, again, so that you see that it comes from somewhere, as opposed to somebody just came up and said, hey, why don't we just throw these things together and call it something?
All right, mister, so what you did before, you put 10 kilograms and it was going 5 rods per second.
I said this point right here was going 5 meters per second.
The other one you said 5
Oh,
rods.
Okay, yes,
That's why we was talking about that's why we was talking about that right there.
okay.
So I'm thinking that we were going to be doing the 2 pi r formula for that, no? But you said.
But that would still, if you did 2 pi r, so that's the circumference of a circle. If this thing spins all the way around, that circle is gonna be different for the outer point than it is the closer you get in, it's not much.
Okay.
So that's. All right, let's sort of go through.
How
Sorry?
about this? I just did that like that and it still gave me the same answer. So I don't even know. Not the same answer, but it gave me like 1.25. Kind of, you know, cause y'all just got 125, I got a point in here.